Here we have two problems concerning the definition of sine and cosine, where I don't have an angle, but I have a complex number z. So we're going to find cosine of z to be equal to e to the iz plus e to the negative iz divided by 2, and where z could be a complex number as opposed to just a real number. First off, let's show that this makes sense if z is real. If z happens to be a real number, then when I evaluate this over 2, that's equal to cosine of z plus I sine z plus cosine of negative z plus I sine of negative z, all divided by 2. And so let's see what happens. Cosine is odd, so cosine of negative z is the same thing as cosine of z. So cosine of z plus cosine of z makes 2 cosine of z. Sine is odd, so sine of negative z is negative sine z. So these two sine terms cancel because the minus pops out. Divided by 2, which is therefore equal to cosine of z. So if z is a real number, then this works out, and so we'll just simply extend the definition if z is complex. Secondly, let's show that the only real roots of cosine of z equals 0 are the ones we'd expect. We know full well that if z is a real number, then these are the only roots of only places where cosine of x is equal to 0. Let's now show the same is true if we extend to complex numbers. So let's solve cosine of z is equal to 0, which means that e to the iz plus e to the minus iz divided by 2 equals 0. So that means that e to the iz plus e to the negative iz is equal to 0. So that means e to the iz is equal to negative e to the negative iz, which is the same thing as negative 1 over e to the iz. So multiplying up, we get that e to the 2iz must be equal to negative 1. And we recall that negative 1 is the same thing as e to the I pi. So we have two complex numbers that are supposed to be equal to each other. The only way that happens is if that 2z is equal to pi plus 2 pi k, where k is an integer. That's the only way that e to the z1 is equal to e to the z2 is if the two different complex numbers differ only by 2 pi, the two imaginary parts differ by 2 pi k. And so dividing, we get that z is equal to pi over 2, or let's combine them, we factor the pi out, and we get, dividing by 2, we get k plus 1/2, where k must be an integer. Maybe positive, maybe negative. And so that is the proof that even in the complex plane, the only place where z is equal to cosine of z is equal to 0 is at the odd half multiples of the half multiples of pi. And again, the basis for this is the statement that e to the z1 equals e to the z2 implies that z1 doesn't necessarily equal z2, but they differ by a 2 pi I times n, or 2 pi I times k. So that's the property of the exponential function that is needed to proceed with the final steps of this proof. Thirdly, let's solve cosine of z is equal to 2. So let's solve cosine of z equals 2. Now clearly, this cannot happen if z is a real number. If z is real, then the cosine of a number must be between -1 and +1. However, that does not apply if z is complex. You could get that cosine of z is equal to 2 if z is permitted to be complex. So we have e to the iz plus e to the minus iz divided by 2 equals 2. So if I multiply up, I get 4 on the right-hand side. Now for the sake of simplicity, let me let w be equal to e to the iz. Then that means that w plus and e to the minus iz is therefore 1 over w. 1 over w is the same thing as e to the minus iz. And you should verify that if you don't believe me, that if you multiply these things together, you get 1. So combining everything on the left-hand side and clearing out the denominator, you get w squared minus 4w plus 1 equals 0. So that, using the quadratic formula, w is equal to 4 plus or minus the square root of 16 minus 4 makes 12 divided by 2, which is 2 plus or minus the square root of 3. Now that is equal to e to the iz, and so therefore I times z must be equal to the natural log of 2 plus or minus the square root of 3 plus 2 pi I times n. So finally, clearing out the z, we get that z is equal to, multiplying by negative I on both sides, we get negative I times the natural log of either 2 plus square root of -3 or 2 minus the square root of 3 plus 2 pi n. And so those are the places where cosine of z would be equal to 2. So there are infinitely many solutions of this equation: negative I natural log 2 plus square root of 3 plus 2 pi n, and negative I natural log of 2 minus square root of 3 plus 2 pi n.